This video introduces the data table as a tool for evaluating a function or a model in an Excel spreadsheet. We will begin by evaluating a very simple function, the equation of a line, and then we'll move on to use the data table to evaluate a more complex model, the exponential smoothing, and finally the adjusted exponential smoothing model that has two parameters. Now there are two types of data tables, one dimension and a two-dimension data table. This refers to how many parameters in the model that we're going to vary. We're going to begin with a single dimension data table evaluating the equation of a line. And of course the equation of a line, y is equal to an intercept plus a slope times value of x. Now if we make the slope of our line 2 and the intercept 10, as we provide different values of x starting with 0, we can identify the value of y. If x is 1, y is going to be 12. If x is 2, y becomes 14. So this is a very straightforward function. But what I want to do is illustrate how a data table can be used to feed various values of x into this function and record y. We're going to begin the data table working in cell D3 providing values of x. We'll start with 0 and increment by 10 all the way through 90. So what I'd like to do is feed these different values of x into the model and record the value of y that results. And the way I'm going to do that is in cell E2 place a reference to y. Now the data table itself is contained in cells D2 through E12. Does not include the column headers up here. I've placed these in here for your convenience. Important things to note is that the values that we're going to feed into the model begin in the second row of the data table. For a one-dimension data table, the top row is reserved for items that we're going to record. In this case, we're going to record the value of y. Now, in order to turn this into a data table, I have to select the entire range, D2 through E12, go to the data ribbon, select what if analysis, and click on data table. Now the dialog box that comes up asks for a row input cell and a column input cell. And the row and column input cell will both be used for a two-dimensional data table. We're working with a one-dimensional data table, so we're only going to use one of these. We're going to use the column input cell because the inputs for the model or the function are arranged in a column. The column input cell identifies where in the model do we send these values. These are values for x. They need to go to the model in cell B3. Now when I click OK, Excel is going to feed these values into the model and record the value of y. So when x is 10, y is 30. When x is 20, y is 50. And I can now use this information to generate, for instance, a line graph to see how this function behaves. Now this is a very simple function. If this function was a little bit more complex, say intercept plus slope times x squared, the data table would again allow us to see how this function behaves. So what we're actually doing is taking a look at the form of the model through the data table. Now, moving to the forecasting spreadsheet, the one-way data table page in this forecasting spreadsheet has a exponential forecast for ticket sales. And this exponential forecast depends on the value of alpha that we choose. On Wednesday we learned about fitness functions. We learned that mean squared error is one means of determining or quantifying how well the forecast fits the observations. And for this particular model, if we use alpha of 0.03, the mean squared error for the model is going to be 1.35. Of course, if we change alpha to say 0.1, we get a different mean squared error because we have different forecast. Now, tracing this back through, we can see that the mean squared error is coming from the difference between the observation and the forecast, which ultimately depends on the value that we choose for alpha. So, what we're going to do is we're going to use this one-dimensional data table that I've started over here to find the best value for alpha. I'm going to plug in 0.05 into the model for alpha and record the mean squared error. Then I'm going to plug 0.1 in and 0.15, recording the mean squared error along the way. And in so doing, I should be able to find the value of alpha that gives me the lowest possible mean squared error. Once again, the data table will be cells F4 through G14, and I would like to record the mean squared error in the data table. So I need to put a reference to mean squared error. Now if I highlight the entire data table, again go to Data, Ribbon, What If Analysis, and Data Table, again I have a column input cell. And once again, this dialog box wants to know where to send the values that are in the column. These are values for alpha. They need to go into the model in cell F2, so I'm going to refer to cell F2, alpha. I click OK, and Excel feeds in 0.05 for alpha, records a mean squared error of 0.53. And then it feeds 0.1 in, records a mean squared error of 2.53, getting better. If I take a look at all of the values of alpha, I can identify that the best value of alpha is going to be around 0.25, giving me a mean squared error of 1.37. Graphically, I can look at how this error function behaves. What we're looking for is the lowest point on the error curve, and that lowest point is going to be around 1.37. And again, I'm going to play with this a little bit. Select data and give myself the input so I can actually interpret this. And I see that somewhere right in this range I've got the low point on the curve, somewhere between 0.25 and 0.3. So I could actually come back to the data table now and change the values of alpha. Instead of incrementing by 0.05, how about incrementing by 0.01, starting at 0.26. Once I have a sequence started, I can continue this through, and I can now see that the low point is right here at about 0.28 or 0.29, mean squared error of 1.34. So what does this tell me? If I want the best fit for this model, I need to use an alpha of 0.28 to get a mean squared error of 1.34. So we have used the data table to optimize a parameter for a model in one dimension, but of course when we go to the adjusted exponential smoothing model, we have two parameters, alpha and beta, that we have to be concerned with. Now, in order to vary both alpha and beta, I'm going to use a two-dimensional data table. We're going to continue using the column as values for alpha. We're now going to use the row as values for beta. And the data table will record the mean squared error for every combination of alpha and beta that I specify in the data table. All I have to do is again put a reference to mean squared error, but what I'd like you to notice here is that this reference to mean squared error is in a slightly different location in the two-dimensional data table. The data table extends from cell K2 through P7. The first column is values of alpha, the top row is values of beta, and the top left corner, cell K2, is the cell that's going to identify what I want to record in this data table. Again, it's a reference to mean squared error. Now I set the two-way data table up in the same manner. I'm going to go to the data ribbon, what if analysis, and select data table. This time I'm going to use both the row input and the column input cell in this dialog box. Row input cell will be beta, these values across the top that are in a row. The column input cell is going to be alpha, values that are along the left of the data table. I click OK, and Excel gives me a two-way data table, values of mean squared error for every combination of alpha and beta. Now, when I get this two-way data table, it doesn't have the shading in it initially. And with a lot of values in a two-way data table, it's going to be a little difficult to find the optimal value of beta, or excuse me, the optimal value of mean squared error. So what I'm going to do is use conditional formatting on the home ribbon. Conditional formatting allows me to apply a color spectrum to a range of data, and the color depends on the value within that range. So the highest value in this data table is 2.95. The lowest value is the greenest, 1.37. I get a mean squared error of 1.37 when I have alpha of 0.2 and beta of 0.2. Now, of course, the true value, optimal value, is going to be somewhere between 0.1 and 0.3. And if I wanted to spend a little bit more time, I could narrow in this range and find the true optimal value of alpha and beta for this particular model. But what you see is that we are using a data table to see how a model behaves in some respect when we vary different parameters in the model. In this particular case, we've used the data table to find the optimal value of alpha and beta according to mean squared error.